Hello everyone. In the last lecture, we had seen the design of the Cotter joint and again design procedure that we can see. So today we will solve problem. So the first problem, it is required to design a Cotter joint to connect the two steel rod of the equal diameter. Each rod is subjected to an axial tensile force. They have given the force, it is 50 kilonewton, and the material of the two rod and the cotter is selected the plain carbon steel. So property of that, it is given the 30C8, it is a designation, and its yield strength they have given 400 Newton per mm. The factor of safety for the rod's pivot end and the socket end is assumed as a 6. So this is 6, and while for the cotter pin which we are using for that, it is taken as a 4. Now assuming yield strength in compression is double that of the yield strength in tension. This is another assumption what they did. Yield strength in compression, that is the sigma C, right? Stress we can consider, it is double that of the tension. Whatever the load taking capability of this material, it is double in case of the compressive load than that of the tensile. So this is one assumption. Then design the joint and specify its the main dimensions. Means we have to find out all the dimensions related to this cotter joint. First we will write what is the given data. They have given the load tensile force, it is 50 kilonewton. So the P equal to 50 kilonewton, and that we will convert it to the Newton. So 50 into 10 is to 3 Newton. Then the material property they have given, the material is 30C8 and its SYT, it is said that is given 400 Newton per mm square. Then factor of safety is 6 for socket and spigot, and factor of safety is 4 for the cotter joint. And another one, that the yield strength in compression is double that of in tension. So this is the given data. Now first we will find out the permissible stresses for the socket and spigot and the rod, because whatever the stress it is given, it is the maximum stress, and here we have to find out the allowable stress which we can allow, and in the design always we go for the allowable stress so that the component it can work safely. Now the allowable tensile stress is what? It is the ratio of the maximum stress SYT, yield strength, divided by the factor of safety. So here they are given 400 Newton per mm square and the factor of safety is 6. So therefore by calculating this we will get 66.67 Newton per mm square. This is the allowable tensile. Now next, allowable compressive stress sigma C is equal to SYT divided by factor of safety, but as they have mentioned the compressive stress it can take double load, so twice into SYT divided by factor of safety, then we will get 133.33 Newton per mm square. Similarly we can calculate the shear stress, so it is always half of the tensile stress, so 0.5 SYT divided by factor of safety. If we put all the value, then we will get the shear stress allowable 33.33 Newton per mm square. Now similarly we will calculate the permissible stresses for the cotter joint, and as the factor of safety is different for socket spigot rod and the cotter joint. So for the cotter joint factor of safety is 4. Now we will calculate the permissible stresses the same way. Permissible stress for the cotter pin is equal to the SYT divided by factor of safety. So 400 divided by 4 will get 100 Newton per mm square. Then the allowable compressive stress is equal to twice SYT divided by factor of safety, will get 200 Newton per mm square. Then the shear stress is equal to 0.5 SYT divided by factor of safety, will get the 50 Newton per mm square. So this is the first step, that we have to find out the allowable stresses based upon the factor of safety. In some of the case, the factor of safety for all these components will be the same, but here specifically they have mentioned factor of safety is 6 for socket, spigot and the rod, and factor of safety is 4 for the cutter joint. So here we calculated the permissible stresses. Now we will move to the design part. Now first we will find out the diameter of the root, and on the diameter there is a tensile stress. So by considering that, stress is equal to force upon the area. As this is the circular one, then we will get pi by 4 d square. Now as they have given the tensile load and already we calculated the allowable stress, that is tensile stress, we will put this value. Then the unknown is what? The diameter d, and that we can calculate easily. So allowable stress tensile, that is 66.67, and the load it is 15 to 10 raised to 3 Newton, and the unknown is d. We will get diameter 30.90 mm, and we will round off it, and nearly about 32 mm we will take. Then next we will move to the thickness of the Cotter pin we have to calculate, and this we are calculating by the empirical relation. So small t thickness of the Cotter pin is equal to 0.31 times the diameter of the shaft, so which already we calculated. So 0.31 into the 32, then we will get 9.92 something, and that we equate or round up nearly about 10 mm. So here we found out the thickness of the Cotter. Now next we will find out the diameter d2 of the spigot. Now again we will consider here first it is the tensile stress induced in this. So therefore again tensile stress sigma t is equal to load upon area. The area which it is resisting to the tensile failure of the spigot already we calculated in the last lecture. So by taking the same, this we will get. Then we will put the value of sigma t allowable tensile stress and the load and the thickness of the Cotter pin already we calculated, and only unknown is diameter d2. So from this we will calculate diameter d2. I will put all this value and we will get the unknown d2. And here by calculating this we will get one quadratic equation, d2 square minus 12.73 d2 minus 954.88 is equal to 0. So we know how to find out roots of this quadratic equation, that d2 is equal to minus b plus minus under root b square minus 4ac divided by yc. Means here how to find out the value of a, b, c. So here value of a is 1, then b is minus 12.73 and c is 954.88. So that we have written here ABC. I will put this value in this above equation. Then we will get the roots of this equation, that is d2, that is diameter of spigot d2 is equal to 37.98, and we nearly equated 40 mm, or around we will round up this, then we will get the 40 mm. Now next we will find out the outer diameter d1 of the socket. Again we know that tensile stress on the socket is equal to load upon the area which it is resisting the failure, that already we calculated. Now we will put the value which already we calculated, sigma t allowable tensile stress it is known, the load applied it is known, and the d2 in the last step only we found out thickness also we know, the unknown is only d1. Now we will put all this value, the tensile stress, the load and the diameter d2, thickness t10, then the d1. Then again we will cross multiply and we will reduce this equation, then we will get the quadratic equation, right, like this. So d1 square minus 12.73 d1 minus 2045.59 equal to 0. Again this is the quadratic equation, and we know how to find out the root of this. Here the value of a is 1, b it is minus 12.73 and c it is minus 2045.59. Then we will put in this equation and we will get the value d1. By solving this we will get the value d1 52.04 mm, and again we will round up it as a 55. See, here you have to take care that we have to round up. So what happens if we increase the dimension, then again the load carrying capacity of the component it will increase. So always minimum requirement is what? 52.04. If you take 53, is again no problem. But always we try to round up with the nearest value. So here the 55 mm, right? So we will get the D1 55 mm. Now next, diameter of the spigot collar D3 and D4 we have to find, and these two diameter we will find out based on the empirical relation. Now D3 is equal to 1.5 times the small d. Small d is what? It is diameter of the shaft, which already we calculated. So we will put this 1.5 into 32, that is the diameter of this shaft, is equal to 48 mm we will get. Similarly, we will find out the D4. It is 2.4 times the diameter of the shaft, and we will put this 2.4 into 32, then we will get 76.8, that is nearly equal to 80 mm. Even here D3 you can take nearly equal to 50 mm also, it is of no problem. But minimum requirement is what? 48. If you go for the higher dimension, you can take it is of the no problem. So means what? If you are increasing the dimensions, means its load carrying capacity will increase, but it should not be too much higher value, near about 4 mm that we are adjusting. The next we will find out the two value A and C, and that again based on the empirical relation. So A equal to C, and that is equal to 0.75 times the diameter of the shaft. So again we will put 0.75 times 32, then we will get the 24 mm. Even you can round up with 25 as it is, or you can put 24 as it is. Next, we have to find out the width of the cotter pin. Thickness of the cotter pin, small t, we found out, and here we have to find out the width B, average width even we can say B, we have to find out. This we can find out by two ways, either by the shear stress or the bending stress. So both we have to consider, and out of that, which is the maximum thickness B, that we have to take value. So first we will consider the shear stress tau is equal to the load upon the area, and there is double shear, so twice P into T. And we know the value given, the load it is given, shear stress allowable for the cotter pin already we found out, the thickness of the cotter pin already we know. So from that you can find out the unknown average width of the cotter pin. So we will put all this value, then we will get the width B, small b, is equal to 50 mm. Now here we found out this based on the shear stress. Similarly, we have to check with the bending stress also. Now we will check for the bending. We know this equation, already we derived this by considering the bending stress, taking moment in the center. So B equal to under root of 3B divided by D into sigma B in bracket D2 by 4 plus D4 minus D2 divided by 6. Here we know all this value, thickness of the cotter pin we know, the bending stress we know, D2, D4, all these parameters already we found out. Now we will put all this, load it is 50 and D2 we calculated 40, D4 it is 80. Now sigma B is what? It is a bending stress, and sigma B is equal to, here we are taking the sigma 2, that permissible tensile stress for the cotter pin. Remember this, sigma B equal to sigma T here, and for the cotter pin permissible tensile stress we calculated the permissible stresses for the socket spigot end and for the cotter pin. So for the cotter pin it is 100. Now we will calculate this, then we will get B equal to 50 mm. Again, if we compare width by considering the shear, it is 50, and by considering bending it is 50. Here both the values are same. Therefore, from this equation 1 and 2, both values are same, so directly we take it as a 50. Sometimes it may happen by considering shear it may get the 50, and by considering bending you may get it is 60. And out of these two values you have to select the larger value. So here Luckily we got the same value, so we'll consider this P equal to 50 mm. Now, if you remember that the socket and the spigot, all this we have designed, or even we found out all the parameters by considering only tensile stress. But while designing, we had seen that all the parts, it may be subjected to the tensile stress, compressive stress, or the shear stress. But right now, what we did, we considered the tensile stress. But here we have to check whether it will sustain in the compressive stress or in the shear stress. That we have to check. And if it is by considering this dimension, whatever the corresponding the compressive stress and the shear stress is less than the allowable stress, then we can say the component which we have designed is definitely safe. Definitely it can take the given load and it can work satisfactorily. Now that we will check. So the crushing stress induced in the spigot end, right? So that we will find out sigma C is equal to P upon T into D2. We know all this value. Load 15 to 10 to 3, thickness of the Cotter pin it is 10, and the diameter D2 it is 40. Now see, it is 125 Newton per mm square, and the maximum allowable is what? 133. So this sigma C crushing it is less than that maximum allowable. Means it is safe. It can work in crushing also. Again, we will check for the shear stress whether it can sustain in the shear load. That the tau is equal to P divided by twice A into D2. We will put all this value. Load it is 15 to 10 raised to 3 Newton. 2 into A it is 24 mm and D2 it is 40. If we calculate, then we will get, by considering this A and D2 dimension, 26.04 Newton per mm square. So this is the stress induced for this given load and of this dimension. Then what is the maximum allowable? It is 33.33 and we got 26.04. So this stress by considering this dimension is less than that of the allowable. So again, this is the safe. It can take the load, it can work easily. Now similarly, we will check the socket end also by crushing and the shear also. How we just now found out that this spigot. In the similar way, we will find out for the socket end. Then sigma C crushing stress is equal to load upon area, that is d4 minus d2 into T. We will put the value, load 15 to 10 raised to 3, d4 it is 80, d2 it is 40, and thickness of the Cotter pin T it is 10. And by considering that, we will get 125 Newton per mm square. Again, this crushing stress is less than that of the allowable stress, that is 133.33 Newton per mm square. So again, it is safe. It can work in the crushing also. Similarly, we will find out for the shear stress, that is P divided by twice in bracket d4 minus d2 into C. We will put all this value and then we will check the induced stress, shear stress in this by taking the dimension d4 and d2 which we designed. Then we will get the stress 26.04. But the allowable stress is 33. So induced stress by considering the dimension is less than that of the allowable. Means again, this design is safe. So the stress induced in the either socket or even in the spigot end, both are within the limit. Whatever the allowable stress we found out, the induced stresses are less than that. So it is the safe. So if the stresses induced is larger, then again we have to redesign and we have to modify the dimension and again we have to change. So in this way we can find out the stresses. Now few parameters again it is remaining that we will find out. The thickness of the spigot collar it is there, T1, that we will find out based upon the empirical relation. So T1 is equal to 0.45 times diameter. Then we will get this T1 is equal to 14.4, that we will equate nearly about 15 mm. Then again we have to consider the taper for this Cotter pin, right? We are taking this one as to 32. So means 1 mm difference in top and the bottom mm when the length of the pin is 32 mm. So this is what 1 in 32. and this we are taking the length of the cotter pin. Usually it is 4 times the diameter of the shaft. If you take the length is equal to 4 times d, then 4 into 32, you will get the length of that cotter pin. It is 128 mm. So this is what the overall the dimensions which we need to calculate. We calculated all, and again we verified by considering this dimension. Whatever the stresses induced in that is within limit, means it can work safely. And after finalizing all these dimensions, we have to redraw that this is the front view, top view and the side view of the cotter joint which we designed. So this is our ultimate aim. We have to finalize all the dimension and we have to redraw this. Okay, thank you.